Hello again, welcome back to Fundamentals of Physical Geography. We're in the middle of a series of sessions right now where we're looking at the impact of energy on materials in the Earth's near surface environment. So we've talked about the Earth's surface, we've talked about solar energy, we've mentioned gravity, we've mentioned energy from the interior of the Earth, and we've talked about the ways that those energy sources impact upon materials to drive processes that give us features or forms at the Earth's surface. And the geography, or the distribution, the patterns of these features and forms of the Earth's surface relate to geographies in the form, the nature, the characteristics of the energy inputs and the materials that those energy inputs are impacting on. In the last session we talked about the energy inputs, so in these next few sessions we're talking about the materials. Today I'm going to be talking about the rocks, the sediments, the soils. In the next session we're going to talk about the atmosphere, and in the following session we're going to talk about the oceans and oceanography. So in this unit we're talking about Earth materials. In the broad sense, that includes all the components of the Earth system, the lithosphere, the hydrosphere, the atmosphere, but we're focusing today on the rocks, the sediments and the soils. We'll talk about atmosphere and the oceans in future sessions. The key points that I hope you'll get out of this session are, first of all, that Earth materials play a central role in physical geography. And the characteristics of those materials make a big difference to the way they behave. And that behaviour, controlled by their characteristics, that's later on going to be crucial to your understanding of Earth's surface processes and landforms when we look at geomorphology. Another important point is that we can use the characteristics of materials, like sediments, to work out the environments in which those sediments formed, or the processes that created them. And that reading of clues, that's central to what physical geography is all about. It's at the heart of research in physical geography. Now, it's important at this stage that you understand what the different materials are and how physical geographers describe them. So you need to make sure that you're clear on the distinctions between a few key terms like soil and sediment, rock and mineral and so on. And this is basic, what I call basic building blocks work for any physical geographer. You have to get this basic material under your belt at this stage. Now, I know that some of you studying this module are also doing geology, so you'll be looking at a lot of these issues in much more detail in the geology program, but here we're just introducing some basic points that's going to be important, that are going to be important to all of the physical geographers doing this course. As always, there's lots of reading available for you to do, lots of independent reading, lots of independent research that you can pursue on your own, but there are some set readings that we've provided out of the basic course textbook that's available online for you through the library reading list that you can access on the KLE. Do try to keep up with this basic reading and consider the lectures or the online sessions such as this. Think of them as just signposting the areas that you need to do some independent research on to build up your individual knowledge of the subject area. The first basic point I want to make is just about the structure of the Earth. And you can look at this in more detail independently afterwards, but just get a feeling for the scale of the Earth, and particularly the very thin scale, small scale, of the Earth's crust. In all of these lectures I seem to find myself talking about energy impacting materials at or close to the surface of the Earth. Well, when we talk about the surface of the Earth, we're talking about the upper part, really, of the Earth's crust. And as you can see here, that's just a few kilometres thick in some places, relative to thousands of kilometres thickness of the Earth as a whole. Also look at the temperature variations. We mentioned these in a previous lecture as well. 7,000 degrees or so in the inner core part of the Earth. Obviously about 10 degrees centigrade today right at the surface where I am. About 1,000 degrees centigrade at the bottom of the crust. So there's a significant thermal gradient through the planet as a whole and through the crust, which is what's driving energy towards the surface that we talked about in that previous session. So here's a closer up view of the outer part of that previous diagram, showing the crust at the upper part here, including both
oceanic crust and the thicker, less dense continental crust, which is the upper part of the rigid lithosphere, below which are the deformable asthenosphere and the rest of the mantle. And for the most part, what we're going to be interested in as physical geographers is happening up in this area, although of course there are driving forces influencing it from below and of course from above. And if you're not already familiar from your previous experience and your background reading with the idea of motion in the subcrustal layer leading to motion in the crustal layer and the division of the surface crust into separate plates that can move around independently, then that's something that you will be encountering in your reading for this session, and you can find out a little bit about from any of the basic textbooks. Again, the geologists amongst you might be getting into more detail in your other subject about the mechanisms that are going on down in the mantle, whether there really are convection cells or whether there are different mechanisms in play. But from our point of view, we're mainly interested in the fact that there is movement in the crust and that connects to processes going on in the subcrustal zone. And this map gives you a broad outline of where the major crustal or lithospheric plates are and some indication of their movement, and you'll see that there are parts of the planet where plates are moving apart. For example, down the mid-Atlantic between the North American and Eurasian plates, they're pulling apart from each other, whereas by contrast in South America, the South American plate and the Nazca plate offshore in the Pacific, they're moving towards each other. And these different plate motions are associated with different sets of processes going on and different kinds of surface expressions of those processes, including differences in the rock types which are associated with the landforms which are being created in those different locations. So there's a geography of geology which physical geographers are very interested in. And this is something else that if you're not already familiar with some of these terms, just go away and look up the terminology that you're seeing on this diagram and make sure that you're familiar with what's going on in this cross-sectional image of a plate, plates dividing, coming together, and surface features associated with those divergent, convergent, and transform plate boundaries. Just make sure that you're familiar with all that terminology when you've completed your reading around this. And this diagram begins to indicate to you the recycling of rock material through this plate tectonic process. So material is being created at this spreading center. New material is arriving at the surface from underneath, and likewise here at this intraplate or mid-plate hotspot, material is being produced at the surface. Then at these convergent zones, material is being subducted back down and is being reabsorbed into the upper part of the mantle for recycling and re-emergence at a later stage. And this gives us the idea of what we call the rock cycle, and we can start identifying within this rock cycle some of the different processes that we're interested in as physical geographers, and also we can begin to pick out where the different rock types that we're going to talk about later on belong. So when we were looking at the bottom of the plate tectonics diagram earlier on, we had material coming up from underneath and producing rocks at the surface, rocks that are derived from a molten state and solidify and crystallize as they cool down nearer to the surface or at the surface. Those are igneous rocks. Along with other types of rocks, those rocks are subject to erosion, weathering, transport, deposition, these geomorphic earth surface processes that we've talked about previously, and they generate debris which can be transported and deposited in the form of sediments, either on land or in water, and these sediments can become lithified or turned into rock by processes of compaction and cementation, and those create sedimentary rocks. If either sedimentary rocks or indeed igneous rocks are then subject to very high temperatures and pressures, they can become metamorphic rock. They can undergo processes of metamorphism, which is processes of change due to partial or complete melting and then refreezing in a modified form. So igneous rocks, sedimentary rocks and metamorphic rocks are connected in that way, and they're also connected to the Earth's surface process part of the cycle, which transforms materials from this end through to this end and leads to them going back down into the rock cycle. On the grand scale, this might also even remind you of things such as W.M. Davis's geographical cycle, where we have uplift and emergence at the starting point, followed by weathering, erosion, transport, deposition, and then a cyclic process of materials as well as landscapes going around in this kind of cycle. So if we're beginning to talk a little bit more specifically about rock-related materials, it's just important now that you start to get your head around some of the basic building blocks, if you like, of this system that we're talking about. And the fundamental building block, before we even start talking about rocks, is minerals. Make sure that you understand the difference between minerals, covered in this slide, and rocks, which we're going to talk about in the next slide. So minerals are the building blocks, if you like, of rocks. Rocks are typically made up of collections of minerals or assemblages of minerals put together in a particular way. They aren't simply a single mineral. A single crystal of quartz here on the right hand side, that isn't a rock, that's a mineral. Likewise, the hornblende, the pyroxene, the olivine, they're different minerals which can be combined in particular ways to make different rocks. And you already know now from the previous slide that rocks come in three broad classes: the igneous, the sedimentary, and the metamorphic. Make sure that you're clear on the differences between those in terms of their origin, and also start having a look at how they're different in their characteristics as well. The geologists will be doing an awful lot more on that, but it is useful for geographers also to have at least a broad idea of the characteristics of these different types of rocks, particularly because those characteristics become important when we start looking at how rocks are one of the fundamental controls, or the geology, the lithology is one of the fundamental controls on the development of certain types of landscape. Karst landscapes, for example, in limestone areas, have the characteristics that they do, largely because of the characteristics of the particular rock, the limestone, which is creating that landscape. Another of the key Earth surface materials that physical geographers are interested in, and this overlaps very much with the bio side of the subject and the environmental science side of the subject, is soil. People often get confused at first between soils and sediments in the same way that people sometimes get mixed up between rocks and minerals. It's important to separate the two of those out. One of the key characteristics of soils is that it includes a biological or organic component. These percentages are going to be variable between different types of soils. This is just a rough indication. But soils include organic material, and particularly soils typically include living organisms, and they are part of the soil, from bacteria right through to the visible things that you're familiar with. If you dig up your carrots, you wouldn't be at all surprised to find worms, and if you look under the microscope, you'll find an awful lot more life in soil. And this is the foundation, or the starting point, for ecosystems and the whole branch of physical geography that we call biogeography. The whole soil science is a big subject in its own right that we could get into, but we're just going to touch on it for now. But a lot of you will be coming back into that area, looking at particular topics later on in this and in later modules. Now, sediments are different from soils. Sediments are what you get when you take some rock and you bash it about, you weather it, you erode it, and you then transport those fragments or particles of broken down rock and you deposit them somewhere so that they're allowed to settle out and become redeposited into the landscape. That's a sediment. It doesn't require any transformation into a living soil by organic activity. That's the difference. Soil has that transformation and organic activity within it. Sediments are simply deposits of fragments of broken down rock that are going through that rock cycle that we talked about previously. This picture shows some volcanic sediments, volcanic ash and volcanic bombs, referred to as tephra, volcanic airfall deposits. And this is in Ecuador, and these are layers of volcanic ash, volcanic tephra, from the volcano Chimborazo in the central part of Ecuador. But you can get sediments in fluvial, aeolian, glacial, to do with rivers, to do with the wind, to do with glaciers. All of these geomorphic processes can deposit sediments, and by looking at the characteristics of the sediments we can work out something about the processes that have deposited them. And there's a volcanologist here photographing this tephra, trying to work out what was going on in terms of the eruptive history of the volcano, or the depositional history of the sediment that led to this particular characteristic of the deposit. So at this stage there's a bundle of things that you just need to be clear about in your head. The differences between rocks and minerals, igneous, metamorphic and sedimentary rocks, the different kinds of plate boundaries, the constructive and the destructive, mid-ocean ridges, island arcs, rift valleys, those various mega landforms associated with plate tectonics. Make sure you understand the differences between weathering, erosion and the general term denudation. Make sure you understand the difference between sediment and soil, and so on. Check out the set reading for this unit, as well as the signposting that I'm giving you within the session, and make sure as you go through that reading that you're picking out some of these key differences and that you're understanding what these different terms refer to. So I'm going to pause at this stage, and then I'll come back in the next video, part 2 of this unit, and we'll look at some aspects of sedimentology, which is one of the very important parts of the physical geographer's toolkit for interpreting landforms and landscapes. So we'll just look at sedimentology and sedimentological characteristics of landscapes as a case study of how we can interrogate evidence from the landscape to try to work out things about what processes have been going on and what factors have been controlling those processes. So we'll do that in the next video.